The question now becomes, how can we make our estimates for area even better? What could we possibly do here? So these numbers should all look familiar. These were all when we had 4 rectangles. But what if we had 10 rectangles, dividing this same interval into 10 equal pieces, and then choosing left endpoint or right endpoint or midpoint of each subinterval, using that as the height, determining the areas of the rectangles, adding them up, and getting these totals. And what if we did that with 50? What are you noticing is happening to the numbers? How do the numbers compare with each other when we have more rectangles? Now we're going to talk about understanding the formulas, the general formulas, the generalizations of these ideas. And we're going to use what's called sigma notation, which is when you use this capital sigma, which is the Greek letter S, and it stands for sum. Remember earlier when we had the right Riemann sum, the right endpoint Riemann sum, we had f of, I'll call it x0, plus f of x1, plus f of x2, etc., plus f of xn minus 1, times delta x. That was our ln. And then Rn was f of x1 plus f of x2 plus etc. plus f of xn, all multiplied by delta x. And then m sub n was f of x1 bar. Remember, the x1 bar notation means midpoint in this case, plus f of x2 bar plus etc. plus f of xn bar, all multiplied by delta x. If I wanted to rewrite, let's say, L sub n with sigma notation, I would write sum from k equals 1 to n of f of x sub k minus 1 times delta x. If I wanted to rewrite r sub n, I would say sum from k equals 1 to n of f of xk times delta x. And then if I wanted to write mn using this notation, I would have summation from k equals 1 to n of f of x sub k bar times delta x. It's just a shorthand way of writing a long sum. Now, what they're saying here is what the xk star is in each case. It's, for the left Riemann sum, it's a plus k minus 1 times delta x. These are just formulas to write in a general way the whole subinterval thing I was talking about earlier. So now the question is, how do we find the exact area under this curve? Well, it turns out that if we take those sums that we talked about in the previous slide, whether it's the right endpoint approximation or the left endpoint approximation, if we let the number of triangles, which is what n represents this whole lecture, if we let n go to infinity, meaning if we let the number of rectangles become infinite, think of what it would mean to have infinitely many rectangles in a confined, finite place like this. Each rectangle will get thinner and thinner and thinner until it's essentially just like a line segment. In other words, you're imagining that you're adding infinitely many objects that are infinitely thin. And that's going to get you the exact area under this curve. Here's another look at the formula. So we have, without the sigma notation, we have that sum of the rectangle heights. If we have n rectangles, we're letting the number of rectangles go to infinity. In other words, we're increasing how many rectangles are fitting in the same interval. And if we let n go to infinity, that's going to give us the actual true area under the curve.